All right. Thank you, everyone, for attending today, our webinar on IoT connectivity challenges with low-power NB-IoT modem solutions. My name is Rich Collins. I'm the Product Marketing Manager for ARC Processors and Subsystems at Synopsys. And my colleague here is also going to present a portion of today's webinar.
Yes, good morning. I'm Ibon Silla, and I'm the Product Marketing and Application Engineering Director at Palmacia. For those who don't know Palmacia, we are a company that is based in Santa Clara, California, with design facilities in McKinney, Texas, Cambridge, UK, and in Hong Kong. So we focus on providing IC and IP for Wi-Fi, emerging Wi-Fi and LTE standards. Thank you, Rich.
Excellent. Thanks, Ibu. All right, let's get started. So just a little bit of background on NB-IoT in general. If you're familiar with kind of the 3GPP standard, there's kind of a broad range in terms of performance, in terms of functionality, and then obviously in terms of the markets and applications that are well suited for those particular protocols or algorithms. Narrowband IoT was introduced a couple of releases ago of the standard, and really it was meant to be kind of go hand in hand with the sort of traditional LTE bands to provide an alternative path for applications like personal medical devices, smart city applications like smart traffic lights, smart street lamps, things like that, where the idea was it would be not a regular transmission to the cell towers like you would have with, say, a mobile phone, more of a periodic transmission, maybe to just update status, things like that. So because it didn't need to update as often as a regular transmission, the idea is that these battery-operated, potentially remote types of applications would be able to use this sort of lower bandwidth, lower power solution. So it's really well suited toward IoT type of applications, and that's why it's called narrowband IoT colloquially. As 5G rolls out, then narrowband IoT will go along for the ride, so to speak. So basically, it is a critical component of the 5G standard. You could actually look at it as kind of almost like a paradigm shift for these types of devices. It's really an alternative to what is used today. Sometimes, through 2G and 3G cellular networks are used for some of these applications. This is a much lower power alternative, and I'll show on the next slide, most of the mobile network operators around the world are building in this support as they roll out 5G over the next couple of years. In terms of growth, there's really an estimated explosion in the market around devices that will support the NB-IoT protocols. Obviously different people have different opinions about what the number is, but you can estimate that it's probably about 40% year-on-year growth over the next 10 years. So in terms of where it's being deployed in the world, pretty much all of the major network operators in China, in Europe, in the United States, North America, are all rolling out NB-IoT in different waves, if you will. Some of them, like in China, are rolling it out as a NB-IoT only protocol. Others, like AT&T and Verizon in the United States, are rolling it out with LTE Cat-M. Cat-M1, Cat-M2 with the narrowband, and that's because there's a lot of similarities between those. Some of the sort of higher end devices like say smartwatches will use Cat-M, and really the biggest differentiator on those is that Cat-M can carry voice in addition to data, where the NB-IoT bandwidth is just focused on data, but they're both deemed kind of low power portions of the 3GPP standard. And like I said, China is largely leading the way. They are driving the biggest growth. There's lots of pretty much all the mobile network operators are rolling it out or have already rolled it out. and there's a lot of chip development that's being done by companies in China to support the narrowband IoT standard. If you look at kind of how this sort of plays out, a typical device that would implement narrowband IoT, really it's providing kind of a path from the RF or front-end transceiver, where the actual communication to the cellular infrastructure is happening, all the way down to the IoT application itself. And so you have kind of this path from the RF transceiver, which is basically doing the actual, in and out of the signals coming from the network, through the baseband PHY layer, then through the protocol layer that's basically converting it to something that basically the application could understand. And then as it reaches the application is kind of the software that's layered on top of, say, the L2 or L3 baseband protocol. And that would be where the applications processor would be doing, sensor fusion or MP3 playback or face detection, gesture recognition, any of those applications that you would typically associate with an IoT type of edge device. So one of the important things that was developed as part of the 3GPP specification was additional power modes that were added. So as I mentioned at the beginning, a lot of what is important about these types of devices that implement the NB-IoT protocol is that they have to be, they're generally battery operated. So they have to be able to sustain their communication links for a long period of time without having to change out the battery. If you can imagine maybe a remote vending machine or streetlights all over a city, it's not cost effective to have to go and replace all those batteries every couple of months. And so it really is important that the battery operation of these types of devices last more than, say, 10 years, so that the batteries don't have to be replaced that often. And one of the ways that is done or help along the way of getting to that is by defining a couple of new power modes. One is power, what they call power saving mode, is defined by the standard, or PSM. And this is basically defining the ability for a device to go into an extended standby period. And so it's monitoring the network for a period of time, and then it can go into a long period of standby. And that might be, an order of days or months even, depending on the application. And then another power mode that was added was called Extended Discontinuous Reception Mode, or EDRX. And this is basically allowing a device to extend the time interval in which it will listen for synchronization messages from the network. And so again, the idea is that you could go into kind of an extended sleep mode for, say, a few hours, especially for a device that only periodically needs to update status information, say, once a day. And then the sort of longer or deeper sleep kind of mode with power saving mode allows the device to basically stay sort of attached to the network, so to speak, but go into these extended standby periods. So these are important. If you look at any device that's implementing narrowband IoT support, they have to support these modes, or else that sort of greater than 10-year battery life is not going to be possible. So what does it look like in terms of a typical SoC that would implement narrowband IoT? Again, this is just the kind of a generic example, but there's usually kind of three parts that we are commonly seeing in devices that are starting to get integrated together with the comms and the IoT application. You kind of have three major processing elements that are coming together. One is obviously the IoT comms portion that we've been talking about and focusing on in this call, where you have the RF is being integrated more and more onto the same SoC as say a microcontroller device that's doing the application. So there's a processing element that's required to manage that communication traffic. Then you have the dedicated processing element for the application itself. Like I said, you have these types of functions like face detection, things that triggering things like voice and face, music playback, those kinds of functions that you would see in an IoT application have kind of a dedicated apps processor, if you will. And then on the security side, we also see more and more that the security portion is becoming integrated onto the same die as well. So instead of having sort of a dedicated SIM card like you have in a lot of cell phones today, more and more that types of functionality is getting integrated, and we call it iSIM or integrated SIM. And that requires yet a different processing element, generally involving much higher levels of security, side channel protection, and things like that. So those are the kinds of things that you see on a typical IoT SoC or a microcontroller. Okay, and then to that end, where a lot of devices are starting to implement or integrate a lot of these functions on a single die, it really begs the question of what that architecture needs to look like. So today, if you look at the say 3G, 4G, even 5G, mobile applications, a lot of the communication portion is sort of separated from the application portion. Part of that is because of the power consumption. The power consumption is much higher. Technology nodes might be different as well. But when you start to look at how a narrowband IoT implementation might look, you might think first off that it makes sense to just take an existing cellular architecture, say for 4G, and then just scale it down. Maybe you would just reduce some of the DSP functionality, maybe remove some of the hardware accelerators. And we are seeing, for instance, some of our competition has done that. They had legacy, 3G, 4G designs, and they decided to take those designs and scale that down. And that may get there in terms of functionality, but it largely is overkill for what's required for the bandwidth for narrowband IoT. And so what ends up happening is you generally have a much higher power and much bigger, from a die area perspective, solution than is really required. And so what we've found is that a better approach is to actually look at it from the perspective of building it from the ground up, where you take a low power processor that does basically control and some DSP, because obviously there's signal processing involved in communications link always. And instead of having a big high-powered DSP, maybe just a low-power DSP with some decent DSP performance, maybe marry that with some dedicated hardware accelerators that will address the typical functions that you will see in these protocols, along with obviously some peripherals as well as digital front end, so that you can marry that with an array of RF transceivers. To address different technology nodes, for instance, that this is actually a better solution and more likely to be able to hit that 10-year battery life. So if you look at kind of some of the differences that I mentioned, we're trying to take a big architecture that has lots of DSP, lots of dedicated RISC cores, lots of hardware accelerators, and pare that down. It really, it takes a long time to get there. It's limited in terms of the flexibility. The standards are changing. So we're at, release 14, release 15 time frame now. Soon 16 and 17 will be closely on its heels. So presumably there will be changes that may or may not be software only, and being able to quickly adapt your processing element to that is important. Whereas on the right-hand side, it's a lot more flexible. So for instance, and we'll talk about it, Synopsys solution here, we have a synthesizable solution basically where we can quickly make modifications as required and quickly respin the IP itself and support the next-gen standards. So that's kind of looking at it from hardware. On the software side, software, again, is critical, and being able to provide a solution that does the PHY layer or layer 1, as well as the layer 2 and layer 3, or the UE, user equipment stack, is critical. And to be able to have a foundation with the base library that can easily be adapted again to the changing standards, but also provide kind of a consistent way that the processing or baseband processing portion of the solution can easily interface with the RF. That is very critical because, as I said, with the introduction of RF being integrated onto the same die as, say, the baseband or the IoT applications processor, then it's critical that that integration happen fairly easily, so that customers that want to integrate that quickly can do that without too much pain and anguish, so to speak. And same with the UE. You want to be able to have a flexible UE that basically more or less looks like sort of a traditional LTE transmission to make it seamless in terms of functionality, but also certification, because all of this needs to be certified if you ultimately want this solution to run on any of the mobile network operators around the world. So when you look at what we've done on the Synopsys side, so basically that low power processor that combines RISC and DSP, we have our EM11D, which is well suited for this kind of application. It has a very efficient RISC core at its heart, a 3-stage pipeline processor, but also combines a pretty healthy amount of DSP functionality for this class of core, where we have, for instance, the XY memory architecture, which you could look at as kind of a pseudo SIMD, where I can load 2 pieces of data in a single clock cycle, which makes MAC operations, where I multiply accumulate in a single clock cycle, pretty efficient. We have what we call Apex, which is our ARC processor extension interface, which is where what allows us to add hardware accelerators and additional instructions if necessary to the architecture to support specialized functions. And in this case, we leverage that by building a Viterbi decoder accelerator that we actually put as part of a product that we build around this processor. So like I said, the 16-bit MAC operations is important for processing PHY data, and having this kind of an architecture is well suited to that. We also have a built-in DMA engine, lightweight DMA engine for block transfers. And of course, everything is, because it's a combination of RISC and DSP, our standard tools all support both the DSP and the RISC side of the processor. Just a little bit of history or background on Apex. So basically the idea is that any of our customers can leverage this Apex interface to extend the architecture. So if they just license one of our cores for any of their applications, they can add instructions or they can pair it with their own hardware accelerators, things like that. And like I said, we're leveraging that in this case for basically trig functions and Viterbi decoding, which we feel having some hardware acceleration can really benefit cycle counts, which translates directly into energy savings. But across the board, we see significant energy savings by leveraging accelerators that can tie directly into the pipeline using our Apex interface. So all of that is kind of background for what we've done. We've actually gone ahead and productized a narrowband IoT baseband controller. Again, it's built around the ARC EM11D core that I mentioned. We pair it with those hardware accelerators using the Apex interface for Viterbi decoding, as well as trigonometric functions like sine and cosine that are typically used for these types of algorithms. We have integrated peripherals as well, things like SPIs and UARTs and GPIO. And then we've built a specialized digital front end as well. And so we've worked with multiple partners, in particular Palmacia, that's part of this discussion today, to really make it easy for our digital front end and their RF transceiver to be integrated together. We've actually had some interactions with other implementations where it was just effectively a bunch of wires that were spit out, and it made it difficult from an integration perspective, if you're the MCU integrator, for instance, to be able to easily match those pieces of IP together and get to a quick solution. And certainly with the combination of Synopsys and Palmacia, we've been able to achieve that, and we show that in a demo. Basically, the other part that's important to remember here is the software. So again, you can easily drop some hardware that leaves it up to the end user to then have to go off and develop their own solution. What we're providing here with this IoT comm subsystem, it's a single product. We're also providing that software layer. So we have the base communications layer that's doing things like interpolation, fast Fourier transforms, modulation, some of the base functions that are needed for any communications protocol. Those are all part of the standard software deliverable that's part of the product. And then we've also worked with partners because we're not, say, L2, L3 providers, UE software providers, but we've worked with partners to make sure that our partner software works very well with our IoT comm subsystem hardware to make it very easy for our customers to be able to integrate and run software stacks on top of our solution. In terms of power, so again, the most critical element, I think, of anything that you build for narrowband IoT is that power consumption. How do you achieve that greater than 10-year battery life? So what we've done inside the subsystem is made a pretty strong power management controller inside the product. And we take advantage of some of the power management that we already have inside the ARC CPU, but also add additional power modes. So we have active, sleep, and standby that pretty much align to the power modes that I discussed at the beginning of the 3GPP standard, where depending on where you want to go, whether it's sleep or basically deep sleep, certain memories are kept in retention, or you may go to where everything is off except the always-on power domain, which is effectively, the minimum amount of power consumption without being fully powered down. So basically providing this flexibility to our customers makes it real easy for them to even use some of this functionality themselves. We even provide outputs from the power management unit within the subsystem so that our customers can actually use it at the SoC level as well to provide some additional power management capability for the chip level. So in terms of key differentiation, so there are probably three main elements of these types of designs that we wanted to address with the subsystem. One I've talked about several times is that power, low power, being able to achieve that 10 plus years of battery life. So basically having some dedicated timekeeping and scheduling in the DFE, like I said, providing some of the functionality that is critical to keeping the power down in any communications type of device. Especially the sample rate conversion, channel filtering, and the scheduling that I mentioned, as well as the power management, multiple power management control and different voltage domains, power domains within the processor and the subsystem. Cost, again, PPA is critical. So building something from the ground up that's going to be smaller, lower power, lightweight is critical for keeping costs down. And then complexity as well. So as the standard changes, or else being able to basically allow maybe an MCU provider that doesn't have a lot of experience in communications to be able to get to the point where they can integrate the comms portion onto their SoC without having to basically, become a PhD in communications to understand that. So that's important. So then looking at kind of how that translates, going back to that original SoC that I had at the beginning of the presentation, you can see that what we've been able to do with the IoT comm subsystem is effectively kind of kill two birds with one stone. So on that generic diagram I showed where you had a processing element for the comms, then you had a separate processing element for the IoT application. And with this subsystem, we can effectively do both in the same subsystem because the communication is not happening. It happens periodically. Maybe it's only once a day or once an hour, depending on the application. There's lots of bandwidth left within the processor itself to run other applications. And so with this subsystem and the DSP capability inside the subsystem with the EM11D, we can run all of those types of functions like face detection, like voice recognition, like gesture recognition, and things like that. On top of the communications protocols, and so that can all be managed with a single subsystem. On the security side, we also have solutions that are based on ARC processors targeting integrated SIM as well, and that combination is critical. That processing element needs to stay generally will stay separate because you want to keep that barrier between the functional and the secure within the device. And then another strong element is having an RF transceiver that is really well suited. Again, low power, simple design, easy to integrate with the baseband, and that's what Palmacia has built. And the combination of our baseband control with the Palmacia RF has made a really solid solution. And I'll turn it over to Ibun, but I'll come back at the end and I'll show a demo that we've actually had running for about a year that we showed off at Mobile World last year, and I'll talk a little bit about that so you can see kind of a real world example of it. All right, Ibun?
Right. Yeah. Thanks, Rich. So, yeah, as you mentioned, we have been working with Synopsys for the last year and a half or 2 years. Last year at Mobile World Congress, we had a platform that we demonstrated there, where with Palmacia's RF front end, to show the solution itself, and it was well received. And I think that the audience will have the opportunity to see it, at least virtually today, at the end of this presentation. So, if you look at Palmacia's transceiver, basically we have a direct conversion transceiver. The direct conversion architecture is pretty much bringing some advantage, and it allows us, to have a very good and strong transceiver and very good performances. So it actually the transceiver is 3GPP compliant with the release 14. If you look at the architecture here, you see the transmitter up and then the receiver down, and we have some external element with a power amplifier and a SAW filter. And the power amplifier that we have here is basically because we have to reach the release 14 is recommending 23 dBm output power, and our transceiver by itself, is outputting 10 dBm output power. And the reason we did not integrate it is because if you are in the CMOS technology and you don't want to have 23 dBm PA integrated, to your transceiver, that can get lots of problems. And those who are familiar with designing RF CMOS know that 23 dBm output power PA, if you integrate it with a CMOS transceiver, it can be really a recipe for disaster because your signal integrity will be really compromised. That's why we put the PA outside, and therefore if the customer want to have 23 dBm, then they can just put the PA outside. That we have different type of PA that we recommend, and then we can just recommend them one, and then they can put those. Our transceiver actually is covering several bands. We have the low band and what we call the high band, and these bands are segmented according to the 3GPP specifications. So we have the low band that is covering from 699 megahertz to 960 megahertz, and the high band that is covering the 1695 megahertz to 2200 megahertz. So there are few bands that we are not covering, but usually the band that we are not covering here are not really. We haven't really seen many customers asking for those bands. But basically, we are covering most of the band that today, are actually in demand. So it supports, the 30, 20, 20, 20, 200 kilohertz bandwidth, more for the standard, that is recommended for the standard, of course. And then we have also, we support several type of interfaces, the USB, the I2C, UART, etc. So those are available with this transceiver. And coming back to the external component, I was talking about the PA, that why did not integrate, but we have also the software that we have there that we is helping, basically helping the receiver to have a better noise figure and a better sensitivity. And if I'm going to be presenting some data later on, that will show the performances that we are getting with this transceiver. So, and if we go to the next, this slide, which is showing actually the layout of the transceiver. So you can see the LDO, the PLL, the TX, the RX, and the different blocks, basically, the LNAs. And this is a fully integrated RX DC offset calibrations. It have been built, on a 56-pin QFN silicon. It's proven on SMC 40 nanometer. So the area that we are covering with this transceiver is 2.5 millimeters square. So, and if you are interested in the full characterization report, actually we have it available. We can provide it to you guys, for so that you can see all the data and all the performances of this transceiver. So let's look at the data that we are having here based on the characterization. For the receiver, for example, we have a noise figure that is turning around 1.5 dB and a sensitivity of minus 128 dB. So that is pretty good, actually, numbers for the narrowband IoT transceiver. And we have an IP3 that is turning around minus 17 dBm to minus 18 dBm. And what is really interesting here is, we have done some testing for adjacent the ACS for GSM. And actually, we are beating the margin. We are beating the spec by 15 dB margin. So basically, our transceivers have more margin. We have 15 dB actually of margin. If you test it against the spec, and also if you look at if we had tested against the ACS. EUTRA also. Therefore, there also we have some good margin there of 8 dB. So basically, we are very comfortable using this device, in the GSM with the ACS EUTRA. So because the margin that we are getting from our device is very interesting. So the transmitter side, we also tested, and we are actually at a 75 dB power range. So we have done some testing also for ACP, and therefore, we have 10 dB margin against the spec. For the EVM, we are actually around 2% EVM. So that's a very interesting EVM actually. So the output power, the TX actually, I'm sorry. Yeah, actually, the output power that I mentioned it before is at plus 10 dBm. So if you want to have an output power that is more than that, we can use, a PA that we recommend, and that will bring it to plus 23 dBm because the release 14 actually is requiring 23 dBm output power. So I think I'll yield back to Rich, for this for the next slide, talking about the demo actually that we have provided at the Mobile World Congress.
Okay, thanks, Ibn. So as I mentioned earlier, the idea of building from the ground up kind of a dedicated embedded solution for narrowband IoT isn't just a concept or slideware. We actually went ahead and built a small form factor demo board to showcase kind of a real world example here. And what we did is we took a piece of silicon that we already had, since this was an early development, and it was basically an IoT development board, and we took the silicon from that effectively has the same ARC-EM core that I mentioned earlier. Basically paired that with an FPGA so we could actually put the digital front end that didn't exist as part of that IoT development board onto this new comms board, and then also put Palmacia's RF transceiver silicon that they have. As Abun mentioned, one of the unique advantages of Palmacia's solution is that they actually have silicon, proven silicon, which is unique to, there are a lot of vendors talking about narrowband IoT, but having real silicon goes a long way. So taking that silicon and putting it on our development board and then building a demo around that. You can see that development board. That's next to a small euro coin. So it's a pretty small form factor board which tries to emulate as best possible the kinds of IoT edge devices that you might see narrowband IoT in. Anyway, and what we did is because we're not at the point where we're actually doing network operator testing yet, we basically got an Amerisoft baseband emulator product and a base station emulator product, and combining a cell phone, an Android cell phone, using the cell phone to connect to the development board that we built, measuring some data from sensors that we put on there. So for instance, we put pressure sensors, temperature sensors, things like that on the board as well. And so you can actually send SMS text messages through the base station that will communicate over narrowband IoT protocol to the board, query for instance, the pressure or the temperature, and then have that communication come back as a SMS text message to the cell phone. We demoed that last year at Mobile World. Actually, it was a slightly larger demo that we had because we were still doing kind of prototyping of the boards. But our plan was to basically showcase this version of the demo, which is the much smaller form factor at Mobile World before it was ultimately canceled because of the current COVID-19 situation. But the idea is that we have kind of a real world working example as opposed to just having, something that's sort of theoretical or in slideware. Okay, so to sum it up, the combination of the Synopsys baseband control IoT comm subsystem with Palmacia's RF transceiver dedicated to NB-IoT is really a very efficient low power solution that will allow customers to meet those low power and PPA needs for those types of implementations. And part of the reason that we're able to do that is through the hardware architecture itself, the Viterbi acceleration that we build into the hardware, that really is all about optimizing the battery life. We also include the software, so we make it very easy for customers to basically marry that with the protocol stacks and the RF transceiver, like the one from Palmacia, and drop in effectively a ready-built complete solution. All right, so that was all that I had. So I guess now we can go to some Q&A. All right, I'll go ahead and read the question out, and then if it's for me or for Ibun, then I can judge that, and we can each answer. So there's one question: in which personal, medical, and fitness devices would NB-IoT be better suited than BLE, Bluetooth Low Energy, that is, which seems to be the main connectivity for these personal devices right now? And what are the pros and cons of NB-IoT for these devices when compared with BLE? I think I don't believe that NB-IoT and BLE are mutually exclusive by any standpoint. They're kind of different use cases, if you will. I see narrowband IoT more aligned with things that don't necessarily want to be tied to infrastructure like a house. With BLE, you're tied to some sort of hub, if you will, right? Whether that's your laptop or it's one of these extended routers in the house or whatnot. BLE kind of hub. Whereas narrowband IoT is more, closer to it's part of the cellular network. So I think it's more suited toward things that want to be kind of out, not be tied to any sort of infrastructure and still be able to communicate with the cloud, so to speak. In terms of personal personal fitness devices, again, I guess that part of that will depend on whether or not it's something as simple as, say, a Fitbit, or if it's more tied to something like, an Apple Watch, where you want to have, cellular types of communications. So I think they're not mutually exclusive. Certainly BLE is strong. There's lots of implementation, lots of development work going on there for building lower power versions of Bluetooth Low Energy and extending the functionality. But I think NB-IoT will have its place where it sort of goes hand in hand with anything that would want to be, have direct cellular communication, as opposed to having to go through, some sort of hub or base. Okay.
Yeah, so Rich, I think that you're absolutely right. They are not mutually exclusive, and also but if you compare them, you'll see that, for example, the NB-IoT would offer a longer range than BLE, and BLE probably might give a better, more data rate. But I think that each of them has a sector or a segment that it plays better.
Okay. How is NB-IoT compared to LoRa in terms of low power and long range? I think my understanding of it, and I'm not an expert on LoRa, but LoRa certainly was there first as sort of a low power wide area network. The advantages of NB-IoT are that it's basically tied to the 3GPP standard. So LoRa had its own protocol, but effectively you would have to build out, the companies that support LoRa have to build out their own infrastructure. So obviously there's some significant costs involved there, where most of the mobile network operators are building out their 5G infrastructure now, and the narrowband IoT kind of comes with it, not for free, obviously, but it's a lower cost thing for them because they're already rolling out these networks. So I think that's one advantage. My understanding is that the range is going to be a lot longer because the bandwidth is different. But as far as power consumption, my understanding is they're pretty much on par. They're both things that need to have extended battery life and want to be integrated into a kind of an embedded controller, so that it's not necessarily kind of its own standalone chipset. All right. Next question. Is NB-IoT viable for usage in industrial environments? That's my understanding. I think that factory automation will leverage narrowband IoT implementations. Certainly there will be standards that need to be adhered to, industrial standards like automotive standards, safety related. But I think in terms of the communication and the protocol, we will likely see it get implemented in industrial environments. All right. A question, it looks like it's about the integrated SIM. So the question was, is the iSIM HSM a third-party element of the SoC or Synopsys IP element? So it is a separate element from the standpoint of It's not integrated as part of the IoT comms product itself. But the one that I did show in the block diagram, the system level block diagram, is Synopsys IP. So we do have a subsystem, an HSM, a dedicated HSM that we call T-Root, that does support with its own dedicated, secure processor that supports side channel protection, hardware crypto engines, true random number generator, and all the software that goes with it, all bundled together in an HSM solution. So we do have a Synopsys solution there that can easily be paired with the IoT comms to give you that combination of communication and integrated SIM. All right. Next question. Will you be sharing the slides with participants by email? So my understanding of the policy is not that the slides will actually just be shared as a PDF, but the webcast will be available so that anybody that wants to review the webcast will see the slides as part of the webcast, but it won't be available as a dedicated slide set. Okay. Is there a viable solution for over-the-air updates for NB-IoT that makes it competitive against Cat M1? I think that, so certainly over-the-air updates will be available, and that's, I think, one of the important parts of having the integrated SIM is to basically, encrypt that communication to make sure you don't have, somebody snooping on that and being able to hack that. I think that the competition against Cat M1, at least the way I understand it, is not so much the over-the-air updates. It's more the bandwidth and what's supported in it. So in other words, if you want voice, NB-IoT does not support voice in addition to the data transmission. But and so that's why you might implement that Cat M1 versus NB-IoT. We do see some customers that are implementing both so that they can basically cover all their bases. But again, the Cat M1 solution is going to be a higher power, solution requiring more processing capability and generally a higher power processing element to manage it. Ibun, do you have any other comment on that one besides, in terms of
yeah, I think that pretty much cover it. So yeah.
Okay.
Yeah, I think that nothing to add. I think that you pretty much cover it.
Okay. Is your narrowband IoT solution available in India? So there's nothing about what we're doing that precludes, effectively it can be deployed anywhere. So there's nothing that says you can't license, for instance, the baseband controller, that IoT comm subsystem is a completely synthesizable RTL solution, so it can be integrated into anything. Obviously, the RF transceiver is for a specific technology node, but there's nothing in terms of specifics for the mobile network operators. Now, we're just releasing the product now, so we haven't yet gone through the certification process to make, to basically go get it certified on the mobile network operators in India. But that certainly, can be done and likely will be done over the next year or so. So I guarantee that there will be plenty of NB-IoT integrations and implementations using the networks in India. Okay. Another question here. Do you see more IP providers building this type of low power baseband, or will the industry try to leverage legacy LTE design? So that was to the point I showed kind of early, where I see some of our competition and is building, kind of trying to scale down an existing LTE design and sort of shoehorn it in, if you will, into something that they can support NB-IoT. And I believe, and Ibun can expand upon it, but I believe that something similar is happening on the RF side, where people are trying to take legacy LTE type of RF support and somehow shoehorn that down into something that can work for NB-IoT. And I think ultimately, my experience talking to customers is that they end up disappointed, because they may get something that can work. They'll actually, it'll actually do the communication, support the protocols, but ultimately they're probably not going to achieve that 10 plus years of battery life for their implementation. Ibn, you have anything to add to that?
Yeah, you're absolutely right. Actually, we have seen more and more customers actually in China and in India that are going for to design for NB-IoT because they realize that if they want to leverage on the legacy, it's going to be an overkill for them, and it's going to be. I think that it's not going to in the long run. It won't be really interesting. So they better have they would rather have a NB-IoT solution, dedicated NB-IoT solution, than kind of leveraging on the legacy. Yeah, I think the legacy is an overkill for the NB-IoT applications.
Right. Okay. All right. Another question here: what extra qualification requirements and costs are involved to bring an IC to market with your IP? So the idea is that we actually want to make it easier for customers to be able to bring their IP. And so our plan is to basically take our solution and go get it certified as a standalone IP, effectively an IP solution at that mobile network operator. Ultimately, though, if you're selling a device, whether that's a standalone SoC or a chipset or a module, ultimately that implementation needs to be certified with the MNO. So in other words, you can't just, even if we go through the entire process and say, all right, our IP has gone through a certification round with China Telecom, as an example, that doesn't mean that you just don't have to do certification for the module that you build around it. You still have to go to the mobile network operator with your solution and get it certified. But it's similar to automotive safety, where the more work that we do on our side to basically make sure or guarantee that the IP has gone through as basically is going to pass the array of RF and power management and protocol types of tests that have to be done to make sure they run, then that's just going to make your life easier when you then go certify the module. So I don't think it'll be, I don't think it'll add any cost at all. I would argue that it reduces cost, because instead of having to do 2 or 3 iterations before you get it right, so to speak, you should be able to get there. If you don't get there first time, it should only take maybe 1 iteration to be able to get there. Okay. Next question. Can you comment further on integrated intrinsic security features to address IoT edge security framework support for end user applications, secure boot device identity? So we certainly could spend a lot of time talking about the security. What I would recommend is basically I can forward this question to our security experts, and they can send you some more detailed information on the integrated SIM solution. Okay. One other question: other benefits to a dedicated NB-IoT RF transceiver or repurposed from other products? So that's that question, Ibn. I kind of alluded to it, where on the hardware side, there are people or vendors that are taking existing kind of 4G designs and trying to pare them down and shoehorn them into an NB-IoT solution. I make the assumption that that's also happening on the RF, but I'll let you comment on that.
Yeah, like I said before, there are some people who are trying to do that, but they realize that it's better for them to design something that is really dedicated to NB-IoT instead of just basically reusing the existing stuff. So yeah, so actually we have seen, like I said, we are working with customers actually in India and China that are actually building some dedicated NB-IoT solutions because they just realized that that's the best way to go. Yep.
Okay. So I think that looks like that's about the end of the questions, and I think we're about out of time. Again, thank you all for attending today. and look forward to maybe talking to some of you again in the future.
All right. Thank you, guys. We appreciate really you coming by.